just to remind you, on exam 3 we did clickers and it was really stinky. We're supposed to be able to do something called self-paced mode, and the newest software doesn't have it, but the older software does. We're going to use that today in lecture for our clicking. And so the practice session that we're about to set up in class, we're going to give you a handout, and you're going to work at your own pace as if you're doing the clicker questions on a test, without me having, and me and Darianne, like we did the other day, cycling through question 1, 2, 3, 4 or 5 times, which is a pain in the butt. We're not going to do that. So today we're going to try it out, see if we can get this older software to work, and hopefully it'll work. And then we're going to use that on the final. So as I said last Thursday, make sure to bring your clicker, your iClicker 2 for the final. Okay, and here's our basic outline today. Our quote from Will Rogers, quite a wise guy. Here's what your mini review for today is going to look like. Just typed out sheet, 3 multiple choice and 1 calculation. We'll give you 10 minutes or so from this. And then when we're done, we'll go through the calculation together. Okay? Turn it to all on. And Megan, you can start handing out those and do that. Do yours over on that side. We're handing out handouts, and just take one and share it either backwards to the back of the room or in towards the middle. All right, we're just gonna do that. So what you can do now is turn on your iClicker, and you'll get a Go Nitro, and then you can start working on this handout. Uh-oh. I think we're on AA. Let's see. Okay, I've got the question. Did you get a Go Nitro? Just welcome. Have you got a square box with the number 1 in it? Yeah. Okay, that means you're on number 1. Okay, just go ahead and start working on it. As soon as you get your hand out, see how this goes. We'll give you 10 minutes for this. And actually, I think I'll do it too. Don't forget to hit the send button. Even though these are multiple choice, you have to hit the send button. Who doesn't have a, Darian, who has extra papers? Raise your hand if you have extras, leftovers. Okay, who doesn't have one? Okay. Morning, we're clicking. Get one of these handouts. Anybody over there have an extra handout? No? Okay. We'll get you one in just a second. Are you done? We need another one right up in the front. Who has leftovers? Go get those.
Who still needs one?
Dare one over here. And hey, you guys, you can keep this handout. Megan, you better start. So it's just a nice little study tool, kind of a mini review. For those of you that got here late, we just did a little mini review, 4 questions to test out the software. I want to go over with you the calculation number 4. So if you got here a little bit late, here it is. Calculate the energy of a red 441 terahertz photon. And the formula to use for this is the Planck relation, E equals HF. And that is the energy relation for photons and stuff. So H 6.62607 times 10 to the minus 34 joules seconds. And the frequency, of course, 441 times 10 to the 12 hertz. And we're going to figure out, we're going to plug that into the formula. By the way, I noticed in discussions, a student was saying, Dr. B, I was using H over MV, but I kept getting it wrong. And because one of the other comments above that had used a wrong value for Planck's, slightly wrong. They got some of the digits mixed up. Anyways, these are the correct digits. And here's the plug-in. Okay, 6.62607. You could use 6.63 if you wanted to. Anyways, 10 to the minus 34, and then joule seconds. And then 441 times 10 to the 12. A terahertz, as you hopefully recall, is 10 to the 12 hertz. And a hertz is the same as a per second, cycle per second. So we're going to use that in just a second. Now, I'm going to show you the calculation as it lays out as if you were doing it, Tyrone, on pencil and paper. All right, so if you know how to use your calculator, you can hit it right here. It's easy to do. But if you're doing it on pencil and paper, here's how I would set it up. I would then write down 6.62607 times 441. In other words, I would take the two numerical parts and just calculate those two together. All right, and that's easy. And then the other thing I would do is handle this exponent. I've got in the top line there, I've got 10 to the minus 34, 10 to the 12, and I'm putting those together into one power of 10 and 10 to the minus 22. And that is because you add the exponents if they're in the same level. You know, if they're both in the numerator, or if you don't have a denominator, you just go negative 34 plus 12, and that's equal to negative 22. And that's why in the red circle, it's a minus 22. And then the last thing that I would do is change this hertz over here into a per second. All right, so I have joules seconds per second instead of joule second times a hertz. Now, the only reason I do this is to make it easy to see that seconds and seconds cancel. A hertz cancels a second. All right? And so my result is, okay, the numeric part, 2922 and change. And then the power of 10 is 10 to the minus 22. And then the unit of measurement is joules. And there's my answer. One more thing. I have to convert it into 10 to the minus 19 joules. And I do that by moving my decimal point 3 spaces to the left and then decreasing the exponent to 10 to the minus 19. All right. So write that down, especially those last 2 lines. If we were doing a written exam, either of those last 2 lines would be kosher. And I would give you pointage for that. On iClicker, we have to specify where to round it off. So on this one, I told you, what does it say here? Type in the energy in units of 10 to the minus 19 joules to the nearest 0.0 times 10 to the minus 19 joule. In other words, if your answer is 1.217 times 10 to the minus 19 joule, then type in 1.22 and hit the send key. All right, so on this one, your answer is 2.922. And so you type in 2.92 on the clicker, right? And let me make a mention to you about something that I mentioned in discussions. You may not have noticed it if you weren't really, reading all the discussions. But when I have clicking questions on exams, and when they're a multiple point item, a calculation usually, so a brain burner that is, worth 4 points or something like that, I can give partial credit if you have a wrong answer. So and I've done the clicker pointage for everybody in here that sent an answer. Now, a bunch of you didn't. All right, you were at the test, but you didn't send in a clicker question. All right, that's your prerogative. Nobody has to answer anything on a test if you don't want to. Everything is voluntary in this class except for breathing. You got to breathe. That's mandatory. But the clicker questions, I combed through all the data. It was kind of tangly and messed up and stuff, but I got it all sorted out and stuff. So everybody's got their grade. And if you have a grade of -1, that means I don't have any data for you at all. If you have a 0, that means either all your answers were incorrect or, well, that's what it means. Okay? And then, but some of you may have like 2 points. Now, on the clicker questions, that means you got partial credit on a 3-pointer or a 4-pointer. Okay? So if you don't have 3, if you don't have 4, if you don't have 7, if you don't have 6, if you don't have 10, you might have like 5 points. So that means you got a little bit of regular full credit and a little bit of partial credit. And I'm very happy to be able to do that because it tells me a lot about what you guys are doing, and I'm happy to give partial credit. Versus, like a Scantron, either it's bubbled in correctly or it's not. There's no partial credit on that, but clicking, yes. Okay, so back to this problem on the study handout. Definitely keep a hold of this. You put your name on it if you want. You don't have to turn this back. Just keep a hold of it. We're going to be doing this similar review with the second lecture student, so it's going to be good. A couple things I want to point out. So these should be some notes for you today. First of all, the photon's momentum is h over lambda, and we can figure out what the lambda is from the electromagnetic wave equation. It's 680 nanometers. So, you don't really think about the de Broglie relation, but you can invert it the other way. I mean, P equals h over lambda. If you know the wavelength, you can use P equals h over lambda. It's no problem. Okay, you can do it either way. And so P is equal to 9.74 times 10 to the minus 28 kilogram meters per second. Now, these are numbers that, we worked out. You worked out the energy, and I worked out 9.74 times 10 to the minus 28 kilogram meters per second for you. so that I could show you this vector here. This is what we would call in relativity the 4-momentum vector. And it has 4 slots. The top slot here is for the energy of a photon. And then the 3 slots below that are for the momentum, the x component, the y component of the momentum, and the z component of the momentum. So I'm assuming that this photon is traveling in the x direction. And that's why I have this picture of a wave packet up here. You can think of a photon as a little bindle or a little wave packet, they call it, traveling at the speed of light, c. In this case, I'm modeling it as going to the right in the x direction. All right. So there's no y momentum, there's no z momentum in these last 2 slots. And this little symbol above the letter P here, it looks like an arrow, but it's really supposed to look like a 4, a sideways 4 numeral, to remind you that it's a 4 momentum. And when we speak about the theory of relativity and the 4th dimension and the fact that we're operating in a 4-dimensional space-time and that our dynamics are 4-dimensional, this is the momentum vector. We call this the energy momentum 4 vector for a photon. And you could do it for any object that you want, a galaxy or a proton or anything in between. Okay, and here's the symbol in large print. P with a little 4 momentum or a little 4 vector symbol over the top of it. And this is assuming that the dynamical state of a moving object in 4 dimensions has to be expressed with energy and with momentum. So this is a fairly simple case of that. It's fairly small. And I'd like to point out one more thing. Number 3, these energy and momentum values for a red 680 nanometer photon. So this one's not a H alpha, it's just 680. It's close to H alpha, but it's a little bit redder. 441 terahertz. This is the amount of energy and momentum that a single one of these photons carries from the sun to Earth. And it's really small, all right? And so every square meter, we know that every square meter about this wide by same height, every square meter facing the sun on the sunny side of Earth gets about 1,361 joules per second through that square meter. Okay, that's why we call it the solar constant. 1361 approximately, according to NASA. Way above the atmosphere, if you take a 1 meter square window, that's how many joules per second are flowing through that window from the SUN. So, it's mostly Roy G. Biv photons. Now, each one of them has a very teeny amount of energy and momentum. So if you're getting 1,361 joules per second from those little teeny photons, that means every second you're getting a lot, an enormous number of photons per square meter. Now think about the entire surface of the sun. We just get, that's per square meter coming from the sun and diluted by the time it gets to Earth, because they spread out as they go through space. But when it's just coming off the surface of the sun, it's just an enormous number of photons. The sun is gigantic, and the number of photons per second in the Roy G. Biv part of the spectrum is truly enormous. It's a huge number. And so we talk about the luminosity of the stars. We really, in an astronomy class, we don't count the number of photons per second, A, because they all have a different energy, and B, because there's so many of them. So normally what we do in astronomy is we compare the luminosity of any star to the luminosity of the SUN. Alternatively, the other way to do that is to compare the luminosity of any given star to the luminosity of Vega, which is a summer constellation star. I don't think you can see it up in the sky at night now. Maybe just before, I could look that up. Maybe just before sun up, but the star Vega, summer in a summer constellation. That's another benchmark. Okay, I'd like to do another clicker question with you, and this one is by way of survey. I just want to double check with you. Turn your clickers on. When you view the e-text, which platform do you use most often? And just type in what your preference is, or which one you use most often. Not which one you like, but which one do you use the most often. And we'll grade all of them correct. And remember that when you do the grading for this. All right, so just take a minute to do that. "30 seconds. Let's see how many people type in an answer. That is interesting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And it looks like most of you, 84% of you, use a laptop or desktop, either Mac or Windows. I was expecting phones, but it's interesting. Anyways, thank you for doing that. All right, you can click that close, right. Okay, let's just go back and do a recap of last time. We talked about how in de Broglie's hypothesis that the quantization of the energy levels, the quantization of the orbits, the granularity, the pixelation of the universe into specific orbits for a bound system is related to the fact that you have to have constructive interference for the electron waves. And that given a certain orbital size, and you worked on a question like that on question number 3, given a certain orbital radius, you have to have exactly one full wavelength along the radius, or maybe 2 full wavelengths, or on up. This one I've got, I found another picture that's a little bit better. It shows you this inner object here, one full variation from a bump to a dip and back to a bump for one circumference. And that corresponds to n equals 1. Then this second one shows 2 bumps and a dip. All right? And it's a little bit better than the graphic that I showed you last time. That corresponds to n equals 2. And then the conceptual diagram extends to n equals 3. And that's just when you've got 3 bumps, 3 dips, and so 3 full cycles of this electron. And so that whole idea of specific orbits and only those is controlled by this. You have to have constructive interference. And then the other part of the Bohr system was that dropping from one of those wavelength states to the lower one, to one of the lower ones, like from n equals 3 down to n equals 2, corresponds to the physical process of emitting a photon of a certain color. And the energy, the difference in the energy levels controls the photon energy, its wavelength, and its frequency, and therefore its color. Bumping up is the process of absorbing a photon. So if you have a photon of exactly the right energy, exactly the right wavelength, frequency, and color, it'll bump an electron for hydrogen or any other atom up to the next, or maybe even up 2 energy levels, or even 3 energy levels. So photons can do that. So it's like a reverse process. When you bump downward, you emit a photon. When you bump upward, you have absorbed a photon. So it's kind of reverse process. Now, the other thing that we talked about last time was phase space, and that a second way of understanding quantization, and we talked about a simple oscillator system, and that mapping out an oscillator as an ellipse in phase space, if you restrict the next ellipse down to the ellipse that differs by exactly 1 h bar or 2 h bars, 1 h or 2 h or 3 h, that's the rule that controls. So this one, we're not exactly talking about constructive interference, although you can certainly do that. This one works for an oscillator system, and in this case, it's easy to see, and it's an exact solution that the 2 ellipses differ in area by maybe h Planck's constant or 2 of Planck's constant, because the area of the ellipse in phase space is angular momentum or action. You know, whatever the enclosed figure, if it's a polygon, a square, an ellipse, or any other shape, the amount of area that encloses is measured in units of angular momentum or action. And Planck's constant, that's really the fundamental unit of area in phase space. Nature, here's another way to put it. The graph paper that nature uses to map out phase space has blocks, each of which is equal to h. That's how nature measures action in phase space, in blocks or bytes of size h. Now, when you drop down to a smaller ellipse, you emit a quantum of energy, and guess what? Its energy is hf, the frequency of the oscillator. Anytime you have an oscillator, a spring, spring with a mass, you have a spring constant k, and you have a mass m, you can figure out the frequency. It's not hard to do, and it's always the same. So if you stretch the oscillator out by 2 centimeters, it'll go to -2 centimeters, back out to +2, back to -2, out to +2 at a certain frequency. If you stretch it out to 1 centimeter, slightly smaller displacement, it'll go from 1 centimeter through equilibrium to -1 centimeter, back out to 1 centimeter, back down to -1 centimeter, and it'll oscillate at exactly the same frequency. And that's what happens here. Every time you drop one energy level, one ellipse, if the ellipse areas change by h or multiples of h, then the photons that go outward are emitted have energy of hf or 2hf or whatever the quantum leap is. Okay, so item number 3 on this, you could easily say, and you could definitely say it, add it to your notes. I don't have it in the notes, but you can add this in. Number 3, these are 2 different ways to look at the idea of a quantum leap. A quantum leap, you've heard it all your life. Wow, that guy's making a quantum leap in technology. I mean, people use that idea of a quantum leap, a sudden and huge leap in achievement or technology or whatever they're using it for. This is the actual quantum leap. This is 2 different ways to think about it, the quantum leap. Now, that's what we talked about last time. I want to talk with you now about the dynamical state of an electron. All right? And this is going to lead us into the periodic table. Would you guys be up for dismissing a little early today? On account of, raise your hand if this is your last class of the week. Ooh, okay. So I'll be up on your good list if I think we're going to dismiss early today. Anyways, let's talk about the dynamical state of an electron. And this is, by the way, dynamical state of an electron interacting with a nucleus is the entire thing that the periodic table encodes. In other words, the periodic table is a table that charts out the dynamical, that has a structure controlled by the dynamical state of electrons orbiting nuclei of all the different elements. All right, now, one of the things that we've talked about are the energy levels of an atom. N equals 1, N equals 2, N equals 3. Now, we talked about that for hydrogen. You could easily do it for helium or neon or any other element, and we have viewed that. Matter of fact, in item C here, 1C, that's how we tell what the energy levels are. If we can figure out the wavelength of a diffraction line, a spectral line that we see in the lab, we get the wavelength. Now, let me map out the strategy for you. Get the wavelength in the lab. Compute the frequency, because frequency is C over lambda. Compute the energy, HF, H times the frequency. And then that tells you the delta EPE in the atom that you're looking at. Right? So you get an idea of the strength of the Coulomb interaction by looking at those spectral lines. So yeah, it's controlled by the Coulomb interaction, of course, constructive interference in accordance with Planck's constant H. And that's what we've talked about so far. Now, what we're going to talk about to get the full specs in the periodic table and really understand what elements do inside of molecules and compounds is to talk about the angular momentum state. Now, an atom we can think of as going around the nucleus, like a little planet orbiting the sun. Now, we know that it's a wave function, and so it's kind of hard to think of waves orbiting the sun, but it's a fruitful way of thinking about it, the electron going around and around and around. Okay, that's orbital angular momentum. Also, something that we know, we didn't initially suspect this, but we found it out very quickly, maybe 90 years ago, 95 years ago, electrons have intrinsic spin angular momentum. So that's 2b, spin angular momentum. We can't see an electron spinning. If you're a baseball, raise your hand if you've ever played a baseball, hardball. Okay, bunch of yous. Okay, and if you've ever played baseball, if you've ever read about baseball, you know that when a pitcher throws the pitch, whether it's a curveball or a screwball or a fastball or a really, really top hitter will be able to look at the seams. Can you see the seams? Have you ever seen them? Yeah. Some people, I don't know how they do it. You have to have like totally eagle eyes, ultra fast reflexes, but you can see the seams. The famous slugger for the Boston Red Sox, Ted Williams, one of the best hitters, pure hitter of all time. He was pretty good out in the outfield too, but famous for batting the last guy to bat 400. Is that still the record? He's the last guy to bat a full season, 400. Yeah. Anyways, Ted Williams, is that true? Yeah. Anyways, he could see the seams. And a lot of guys, they say, yeah, I could see the seams on that coming at me and stuff. And you see the way the seams are running, you can tell the direction of the spin. If you can tell the direction of the spin, if the seams are going clockwise or counterclockwise, that tells you if it's going to break right or break left, or if it's going to cut down and to the left or up and to the left, or any other direction. Well, I don't think they break up that much, but anyways, you can tell the spin. You can see something that tells you the spin state. And then, of course, you can, even if you can't see the seams, you can still see the curve. You get deceived by it. Actually, I should say, you don't see the curve. You swing and you miss because the curveball tricked you. But the fact that you were tricked You swung where the baseball wasn't, means that you've detected spin for a baseball. Now, we can detect spin for an electron, but we can't see the seams. So for that reason, we call it intrinsic angular momentum. So for 2b, write in the word, this is intrinsic. We cannot see the seams. We don't see the structure of an electron. We have tried. We have tried to probe the structure of a proton, and we know that a proton has structure. It's composed of 3 quarks. And that's a whole other week of physical science 1121. So protons, yeah, they have structure. We haven't figured out the structure. We don't think there is a structure. We think it's... Electrons are mysterious. The other thing that's mysterious are photons. Photons are extremely mysterious. I mean, electrons are particles that have wave properties. They're waves that have particle properties. And we think of them as, baseballs that behave with wave properties. But a photon has wave properties and particle properties, and it's extremely unusual. First of all, if you were riding on an electron, you would still have a sense of time. But if you were riding on a photon, your clock wouldn't be moving at all. There's no sense of time. Photons experience no time. It's nobody, not even Einstein knew how to savvy that, but it's true. Anyway, so electrons, spin angular momentum, we cannot see the seams, so we call it intrinsic. There's something about an electron that it gives it a spin angular momentum. Now, the fine details of the H alpha line, so for instance, if we look at really precise diffraction gratings and ultra precise measurements in the lab, yeah, we can see that H alpha can be split. If you put the hydrogen, H beta can be split. H beta, the bluish line can be split into 2. If you put the hydrogen in between the poles of a big, strong electromagnet. So we can pick up the spin. We can see that the electron is spinning by the effects, really fine details of diffraction lines. Okay? So the periodic table, as I mentioned, encodes all of that. All the different factors that you see in a periodic table. And there's different versions of periodic tables. Some of them are just the symbol and the atomic number and the atomic mass and then the name of the element. Others extremely fancy. This one's pretty basic that you've got here on the screen. Now there's a really cool resource, webelements.com. So write that in your notes and put a big star next to it. It is there's probably a bunch of other places to look up the properties of all the elements, but this is the one I like. I use it a lot. Webelements.com. And it looks like this, and it's got all the elements, and each there's vertical groups, and then there's horizontal groups, of course, or horizontal organization and vertical organizations, different colors and stuff. And if you click on any of those, you can see specs, all different kind of properties. So for instance, if you click on, let me get my cursor, Fe, element number 26 there, kind of in the middle, on the 4th row down, element number 26, Fe, that's iron. You can click that and you'll see the density of iron. You'll see its specific heat, its melting point, its boiling point, all that kind of stuff. You'll see how many protons are in the nucleus, how many electrons. So yeah, the periodic table and everything that we're about to talk about for the periodic table, all the properties are related to what the electrons are doing, and that is all encoded in the energy and the angular momentum states of the electrons for every, and if you think about it, a hydrogen atom, the nucleus is just one little old proton, but iron has got 26 protons in the nucleus. So every electron orbiting an iron nucleus is really strongly bound, because it's an electron interacting with 26 protons down there in the nucleus. Versus hydrogen, it's a little floatier. It's attracted, it's bound, but it's just one proton that it's bound to, so it's a little weaker interaction. Now, let's keep going. Let's talk about what elements are. I love this picture. It's a picture, it's basically a sunrise over a snowy valley somewhere. I can't remember where this is. And let's talk about what elements are. Humankind has had this conviction since the days of old, since the days of the Greeks and before that probably, that the universe is made of basic building blocks. I mean, we just seem to sense that. We know that the universe has order. We know that you can make order by having specific blocks of matter. Just like building a house. You use bricks. You need a certain amount of bricks, and if you have bricks, you can order it and do what you want. So, for instance, in this image here of this sunrise, how much hydrogen are you actually looking at in that picture? Now, think about it. Think about all the hydrogen. Now, first thing in the foreground, at the bottom of the picture, you see trees, pine trees, green, pine trees, vegetation. Now, nobody goes around eating pine tree. Well, I suppose beavers do, but pine trees are carbohydrates. Carbohydrates, CHO, carbon, hydrogen, oxygen. So there's a lot of hydrogen in those pine trees. Okay, SNOW, snow. That's that white stuff. And as many of you Floridians may, it's not a myth. It actually has been observed many times. SNOW, snow, crystalline H2O, hydrogen. 2 hydrogens, 1 oxygen. All right, so just in the snow. The clouds. Clouds are micro droplets of liquid H2O. And they're up at a certain level, and at that level they're small enough and they're cool enough that they stay liquid, but they don't, come down to Earth. Although some of them did come down to Earth, they condensed and formed snowflakes and fell to Earth. But a lot of them are still up there in the clouds in the form of liquid droplets of water, micro droplets. The atmosphere itself, not much hydrogen in our atmosphere. But there's one gigantic blob of hydrogen in the middle, well, kind of on the left there, of this diagram, of this image, and that is the SUN. The SUN is mostly hydrogen, a little bit of helium. And the reason that the sun shines is because the hydrogen nuclei in the core of the sun are being fused together, thermonuclear fusion. And they're fused together into a helium nucleus, and that process produces a lot of heat, causes the outer layers of the sun to glow incandescently and provide all the Roy G. Biv light that gets to Earth. So there's a lot of hydrogen in this picture, but the ancient Greeks didn't know anything about hydrogen, but they still had the conviction that the universe was orderly and could be thought of something built from basic building blocks. Now, here's the first guy that developed this idea of elements, the elements of nature. Thales of Miletus, about 600 BC. An interesting guy, pretty smart. Very mathematical, very smart in all the subjects. Aristotle, he could take Aristotle to the woodshed if he had to. If Aristotle misbehaved, it would have been Thales that would have said, okay, straighten up. Aristotle, you're a big guy, fancy guy, but I'm Thales of Miletus. I'm the one that started it all. The first main mathematical and philosophical thinker in Greece. And his conviction was that the basic element of nature was water. Everything was made. Now, he lived in an island in the Aegean Sea. Right? So water was all around him. They got a lot of rain. He watched vines grow and olive trees and grapevines and wheat and all that stuff. So that was his conviction. By the time of Aristotle, the list had grown. It hadn't replaced water. They still said water, but Aristotle, in his day, a couple hundred years later, his thought was, okay, water, but also earth, air, and fire. Right? And up until the time of about Sir Isaac Newton, maybe a little bit before that, when just as Galileo was demolishing the Aristotelian system of motion, other scientists were demolishing the earth, air, fire, and water theory. Okay, let's see if I can jiggle this. Sorry. Come on, display. I just moved the thing a little bit. Did it just come up?
It flickered.
Come on, baby. I moved this just a little bit. It's burning my grits.
There we go.
All right, there we go. Now I'll try to be a bit more careful. Okay, by the 1800s, so this is after Newton, and through the work of guys like Michael Faraday, in the mid-1800s, they were thinking about 60 elements. So they knew about sodium and carbon and stuff like that, hydrogen. And of course, today, the periodic table has over 100 elements. So we've been working on this whole idea, the elements of nature, for quite a while, several thousand years, and we're getting better and better at it. Now, one of the big superstars of the theory of elements, the atomic theory, is John Dalton. 1803, he conceived of the elements as being indestructible atoms, but of course, it was the Greeks that actually formed the idea of atoms before him. And the entire word atom means something that cannot be cut. And his conviction was that the atoms themselves could not be cut or destroyed or broken apart. Now, today we know that that's not true, but that's how he thought of them. And they are hard to, splitting the atom is not easy. Okay? We now know that it's actually possible, but calling them indestructible is a fairly good view of things. That each atom of an element is identical and not reducible to any other element, or to any, you can't divide it, so it's not cuttable down to anything smaller. Now, oppose that, and this is not in the slides, but I'd like you to add it, so this would be number 7 in this list. Oppose that to the idea of a compound, like water, H2O. They knew in Dalton's day, in the 1800s, that water could be broken apart. Water was not an atom. It was a compound. It was composed of hydrogen atoms and oxygen atoms. They could break it apart with electric current, electrolysis. That's how you break apart water. And we still do that today. When we want to manufacture hydrogen or oxygen, we pour some electricity through it, and we get we break the hydrogens apart from the oxygens. All right. So John Dalton was one of the guys, and I'm going to set up some reading for you for homework. Actually, I think we've already had a little. Have we had a blurb about John Dalton in the additional reading? Yes, no, maybe. You guys haven't done any of the additional readings. Okay, good. We'll have some. So now let's get to the periodic table of elements. Dalton didn't know anything about the periodic table. I mean, they all had their lists, they had notes, but nobody knew how to figure it out and kind of get it organized. They knew that there were patterns, but nobody really got the idea to organize them until a guy named Mendeleyev. And he said if you correlate the properties of elements based on their atomic weight, then there does seem to be a repeating pattern. And that's what Professor Mendeleyev from Siberia figured out. And he started working on this in the mid-1800s. Very smart guy. Here's what his periodic table looked like in his day. So he had it organized horizontally, whereas we have it organized more vertically. And he didn't have all the elements that we have today. But see, for instance, right over here in the first column, he has lithium and then hydrogen right above it. All right? And then right next to lithium, Li, he has sodium, Na. All right, now we still have that in the periodic table, but we've arranged it differently. This looks a little bit like our periodic table, rotated 90 degrees. That's all right. That's how he was thinking about it. We now stack it up differently. But the other thing that I'd like to point out, he was going by the basic properties. You know, the density, the boiling point, things like that, the stuff that you can measure in a lab. And he didn't know, he was well before Thomson and Rutherford. He didn't know anything about protons, neutrons, and electrons. All right? But by properties, yeah. And one of the other things about his periodic table, if you look at it over here, there's a gap, all right, between mercury, Hg, and gold, Au. All right. You know, he's got gaps. It's one of those things. Now, let me give you the specs on what atomic weight actually is. It's basically this, the sum of the proton, neutron, and electron masses. And it's unfortunately that they call it atomic weight. It should be atomic mass. In some places you see the atomic mass or the atomic mass number. And basically what we do now in the periodic table is we count up the number of protons. We measure everything in terms of protons and neutrons. Protons and neutrons are very close to the same size. So the atomic mass unit is equal to basically the weight of one neutron or one electron or one proton. Our electrons are very, very teeny, but we still try to measure the mass of those babies as well. Okay, the modern periodic table, figure 10.1 in your textbook, and you guys are in chapter 10 now. The modern periodic table goes by atomic number. Now that is something that they could not figure out in that day. Well, not very easily. And here's a slice of what we have today. Now you can see that hydrogen and lithium, Li, are next to each other. They're stacked up. And here's sodium down here. So Mendeleyev was on the right track. But you know, where he was going horizontally, we now go vertically. And so this is the left side of the periodic table. This first column is called the alkali metals. The second column is called the alkaline earth metals. These are all metals over here. So magnesium is a metal that burns. Sodium is a metal that explodes if it comes in contact with water, I believe. Water vapor in the air will cause a chunk of metallic sodium to explode. So you have to be careful with. Here's the main arrangement of the periodic table. And in the periodic table, you see a bunch of numbers and symbols. And we're going to try to go through that with you right now. And hopefully we'll dismiss a little early. All right, here's a little chunk of the periodic table. And actually, this is from right down here. Let's see, right in here. This column here, copper, Ag, that's silver, and Au. Au there, Jordan. That's a physics joke. Au there. Gold. Gold, Au. I'll just make a corny joke. I have like about 3 corny jokes in total. Here's the other 2. What did the acorn say when it grew up? Geometry. Geometry. Brandon, I'm sorry, man. It was pathetic. It's pretty corny. Okay, so I won't give you the third one. I'll keep that one in reserve. Anyway, so here's a little slice of the periodic table. Okay, and one of the things that they do is give you a lot of times you'll see just the symbol, Cu for copper, Ag for silver. Sometimes you'll see the symbol and the name. And let's compare this. These ones are stacked up vertically in the modern periodic table. Here's Mendeleyev's, and you can see that over here, there's lithium and sodium that I mentioned before, and they're stacked up horizontally for Mendeleyev. And over here, here's copper, silver, and then, oops, you got a little detour down here. In his preliminary periodic table, gold kind of dips down a little bit, 197, and silver 108, and copper 68.4 or 63.4. Now you can see that over here, gold 197, and he knew 197. We now have it to 5 significant figures. Silver 108. And we have it to 5 significant figures. He had 3 significant figures. Copper, 63.4. He was a little low. But we've got it to 5 significant figures now for copper. Notice also that there's a gap. And matter of fact, go ahead and make a note. Mendeleyev's gaps. Mendeleyev's gaps. 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 G-A-P-S. Mendeleyev predicted that in the gaps, someone would find an element. If they looked in the right place, whether in a deep mine or maybe the surface of the sun for helium, that's how we found out helium. He said, there's gaps here that if we look, we're going to find something. All right? And so let's take a closer look. Here's this thing. So there's all kinds of gaps in this. And by God, they filled in the gaps. We have elements there now. And matter of fact, that's one of the reasons that Mendeleyev became so famous, because his theory predicted stuff. You're going to find an element here. He even predicted the properties of those elements. And eventually they found them. A bunch of them they found in Sweden. Some of the rare earth elements were found in Sweden that verified Mendeleyev's periodic table. All right, here's another little blurb for webelements.com. And you can, just go and click on it. Now, let's look at a single tile. Let's look at the tile for Au there, gold. All right, now the name of the element and its chemical symbol are customarily inside each tile. Now, this number down here, that's the atomic weight. All right, so that measures in atomic mass units, AMU. So make a note of that, atomic mass unit, AMU. It's in your textbook, AMU. It's roughly, it's 1/12 the mass of a carbon nucleus. And carbon has 6 protons and 6 neutrons. Okay, so the atomic mass unit is exactly 1/12 of that. Anyways, if carbon is exactly 12, then gold is 196.97 for most gold that we find in this big wide world. Atomic number is 79. Now what that means is the number of protons. So make a note, the atomic number tells you how many protons you have got. For gold, all gold nuclei, 79 protons. And this is where the periodicity actually is. You know, Mendeleyev was thinking of periodicity here in the atomic weights, and he was looking for the right thing, but the real thing that showed periodicity was the atomic number, even better. So think about this. The mass, the nucleus of a gold atom is about 197 somethings, protons and neutrons. Right? So make a note of that. The nucleus of gold has 197 neutrons and protons put together. That's what the atomic weight tells you. It doesn't distinguish between protons and neutrons, but the atomic number does. Right? The atomic number tells you how many protons. So if you look at the atomic weight and round it off to a whole number, in this case 197, and the atomic number, you can figure out how many protons and how many neutrons. Matter of fact, let's try that out. How many neutrons are there in a typical gold nucleus? All right, go ahead and answer this question. The atomic weight down at the bottom is the number of protons plus neutrons together. And the atomic number, 79, is just the number of protons that you've got. So how many neutrons we got? Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And looks like you guys got it right. For those of you that missed it, go ahead and write that down. 197 minus 79 is 118. So that's how many neutrons. Now, hydrogen doesn't have a neutron. Most of the hydrogen in the universe is just one proton. Occasionally we see a hydrogen with a neutron in the nucleus, and every once in a while, a hydrogen with two neutrons in the nucleus. Okay, they're pretty rare. But gold, yeah, we get a huge bunch of neutrons. And every element is different. You look on the periodic table, a lot of the periodic table actually encodes the nucleus as well. But some of it is, quite a bit of it, the actual structure is controlled by electrons. My wonderful students, it has come to my attention that this is the last class of the week for many of you. I shall therefore do two things at the present time. I will not give you homework, but I will dismiss right now, 10 minutes early. See you next week. No homework.
For this one, how do you select more than one correct answer?
It's not letting me?
No, I better.
Oh, okay. I don't know. Let me try to stop this here.